How's it, guys? Welcome to another episode of What Matt Says. Today we're going to be taking a look at a maximization linear programming example. First, we will observe the scenario we wish to solve and then identify the objective function which will return our final result. Thereafter, we will mathematically define the existing constraints within the scenario and plot them graphically in order to find our optimal solution. In this scenario, handy manufacturers produce tables and chairs. Tables sell for $30 while chairs sell for $22. The material costs per table is $13 while the material cost per chair is $9. Labor costs per table is $6 and $8 per chair. The building time for each table is 1 hour while the building time per chair is 2 hours. Varnishing time is 1 hour for both tables and chairs. Handy manufacturers may produce as many chairs as they'd like, but only 40 tables per week. In any given week, there are only 120 hours available for building purposes and 80 hours for varnishing purposes. The question now is how many tables and how many chairs should handy manufacturers produce in order to maximize their weekly profit? The unknowns that we want to solve is the number of tables and the number of chairs. These will be our decision variables, where x1 equals the number of tables which are produced every week, and x2 represents the number of chairs that are produced every week. From this, we can now create our objective function. If we call z profit, we know that we want to maximize z, which is equal to the number of tables times by the profit, which is what the table sells for, minus its two costs, the material cost and the labor cost, plus the number of chairs times by its profit, which is what it sells for minus its material costs and labor costs. We end up with an objective function where the profit is calculated as 11 times the number of tables produced every week, plus 5 times the number of chairs produced every week. For our first constraint, let's consider the number of building hours. We have been told that we have a total number of 120 hours per week for building purposes, and every table takes 1 hour to build and every chair takes 2 hours. So for every table, it's going to be 1 times the number of tables, x1, plus 2 hours times the number of chairs, x2. This must be less than or equal to the available 120 hours we have for building. In a similar fashion, a constraint can be defined for the varnishing hours available, which is 80 hours per week, and with 1 hour of varnishing required per table and 1 hour required per chair, we know that 1 hour times by the number of tables, x1, plus 1 hour times the number of chairs, x2, should be less than or equal to 80 hours. We were also told that the maximum number of tables that can be sold in a week is 40. This means that x1, the number of tables produced every week, may not be larger than 40. However, there is no limit to the number of chairs that can be sold, and therefore there does not need to be any constraint applied to the variable x2, the number of chairs produced. Finally, we apply our logic constraint, which is to say that we cannot produce a negative number of tables and chairs every week, and the count of tables and chairs are of the type integer, since we cannot sell a semi-complete product. Now, with all of our constraints ready, we may begin to plot these constraints in order to get a graphic idea of where they lie and how they behave. In this example, there are only 2 variables which exist in the respective constraints, which means that we can develop a 2-dimensional plot of x2 versus x1. Taking a look at our first constraint, if we make x1 equal to 0, we can find our x2 axis intercept, which is to say that it would be 120 divided by 2, so it would intercept at the value 60. In a similar manner, we would say x2 equal to 0 in order to find the x1 axis intercept, which would then be 120. We also need to keep in mind which side of the line our feasible solution space exists on, because in this scenario our result is less than or equal to 120. We know that the feasible solution space is below the line. Once we have finished plotting all of our constraints, we are able to see the final feasible solution space as indicated in orange. This means that only values of x1 and x2 lying within that space meet the conditions set out by the scenario. Remember that variables x1 and x2 are integers. The dots shown within the feasible solution space represent all possible solutions. Now, in order to find the maximum profit, we use the objective function. We rearrange the objective function in terms of the vertical axis x2 and look for the gradient value sitting next to the horizontal axis variable x1, which we see here is negative 11 over 5. Plot this gradient as a dashed line on your plot. Alternatively, substitute any value in for the solution z. When in doubt, just multiply the coefficients together. We have coefficients 5 and 11 in this example. When multiplied together, this makes 55. Make x1 equal to 0 to solve for the x2 intercept and x2 equal to 0 to solve for the x1 intercept. While staying perfectly parallel with the dashed gradient line, slowly move away from the origin until you reach the very last point of the feasible space. This location of variables x1 and x2 will produce the largest profit for our objective function. By substituting the found values x1 is equal to 40 tables and x2 is equal to 40 chairs into the objective function, we can see that the maximum weekly profit for handy manufacturers will be $640. If you found this to be a helpful introduction into linear programming, please like and share to your friends and colleagues. Although this channel is young, subscribe for future content, and good luck with all your work and studies. Bye for now.